Hello everyone, welcome to my YouTube channel MechE-FUNdaMENTALs. In this video, the topic is elastic deformation. In the series of Fundamental of Mechanical Engineering, the topic is elastic deformation, in which I will discuss the elastic deformation due to axial load, principle of superposition, and a numerical. Now the first, that is the elastic deformation in a body due to axial loading. Now you see this diagram. We have a bar of length L, A is the area, and E is the modulus of elasticity of that material. And in this bar or rod, we have a load P in the axial direction. So this is the axial loading. And now due to that axial loading, delta is the elongation. So that we have to find out. So as it is the elastic deformation, so we can use the Hooke's law. And from Hooke's law, we can easily get a simple relationship for the elastic deformation of a material that already I discussed in previous videos, that the stress is proportional to strain. And that proportionality is replaced by a symbol E, which is known as the modulus of elasticity. So sigma is equal to E into epsilon. And sigma, that is the stress. Sigma is the stress. So here P is the applied load. A is the area of the rod. So stress, by definition, it is force upon area, P upon A. E, that is the modulus of elasticity of the material, and that is the property. And epsilon, that is the strain. And strain is what? That is the change in dimension to the original dimension. So change in dimension, that is the deformation or the elongation, that is delta. And L is the initial dimension or the initial length. So strain is delta upon L. So this is the Hooke's law. Now we arrange the equation in such a manner that we get a value of delta, that is the elongation, that is PL upon EA. So P, that is the axial load. This is the axial load. L, this is the initial length of the rod or the bar. E, that is the modulus of elasticity, that is also known as the Young's modulus, that is the property of the material, and it is given to us. And A, that is the normal area. So with the help of this formula, we can find out the elastic deformation in a body due to the axial loading. Now the next is the principle of superposition. And according to this principle, on a linear elastic structure, the combined effect of several loads acting simultaneously is equal to the algebraic sum of the effects of each load acting individually. Okay, now you see this situation here. We have the two sections 1 and 2, and this is the combined geometry made by these two sections, and F is the applied load in this way. So now here we have to find out the total elongation or the total deformation in that particular structure. So here we use the principle of superposition. So according to this principle, we have to check the individual effects of these sections, and then we have to sum up, and that sum is the algebraic sum. It means the individual section, it may be elongate or contract, that depend. If the body is under tension, so that will elongate. If the body is in contraction, that will, its length will reduce. So we have to do the algebraic sum, means we have to use some sign convention. Let us suppose for the elongation, if the body elongates, we take the positive sign. We take the positive sign. If the body will contract, the length will reduce. Then, and that is due to the compressive load, we use the symbol negative. So that is the algebraic sum. So that we have to check. As the whole body is under equilibrium, so that is the governing equation for any deformable body. When the body is under equilibrium, then only we have the deformation. You see this structure, F, this load and this load. You see here we have the two external loads, and you see the body is under equilibrium because magnitude is same, the direction is opposite. So the whole body is under equilibrium. Then only we have the deformation or the body is under stress. So now we apply the principle of superposition. So first we have to separate these two sections, and then we have to draw the free body diagram of these two sections. And definitely, if the whole body is under equilibrium, so individual sections also must run under equilibrium. So here you see this F is the load acting here, and this F is the load which is acting here. If these two individual sections are in equilibrium, so in this particular section, the left side force is F towards right. So definitely we have a force in its right phase in the leftward direction. And if this body is under equilibrium, so definitely this F1 that is equal to F. In the same manner here, this section is also under equilibrium. We have a force F on its right phase towards left. So definitely we have a force on its left phase towards rightward direction, and definitely this F2 is equal to F. So F1 that is equal to F2 and that is equal to F. So by using the equation of equilibrium in the individual sections, we can find out these hidden forces actually, because they will appear. These are the internal forces which will appear when we separate these sections to make that particular section under equilibrium. Now according to the principle of superposition, delta is equal to delta 1 plus delta 2. So delta is the total deformation and delta 1 is the deformation in the first section, delta 2 is the deformation in the second section, then we have to sum up. So that is the algebraic sum. So that we have to see the body elongates or contract. So accordingly we have to put the sign. In elongation we take plus delta, and in the compression or in the contraction we take negative sign. So finally delta that is equal to delta 1 plus delta 2, and I already discussed the elongation expression, delta is equal to PL upon AE. So with respect to the first section, that will be F1 L1 upon A1 E1, and with respect to the second section, that will be F2 L2 upon A2 E2. Okay, so in this manner we can use the principle of superposition. Now here I discuss a numerical to understand the principle of superposition. So this is a uniform steel bar as you seen in the diagram. It has a diameter of 50 mm and it is subjected to the loading as shown in the figure. And here again we have to find out the elongation, and here we are assuming the modulus of elasticity of the material is 200 gigapascal. Okay, now you see this diagram. So this is a steel bar and you see it is fixed on its left end. So this is the fixed support. We fix it, and 80 kilonewton, 40 kilonewton and 70 kilonewton, these are actually the external axial loading in different sections or different point. Okay, so now I already told you that if we have the deformation or the elongation in any body, then it must be under equilibrium. Okay, so now what we see, we have these three forces, 70 kilonewton, 40 and 80. You see the directions also, and because we are fixed that rod on its left face, so definitely we get some reaction from there. Okay, so to find out that reaction, we have to put the condition of equilibrium. So R is the unknown force or the unknown reaction. The known forces are 80 kilonewton, 40 kilonewton and 70 kilonewton. So by applying the equation of equilibrium, so what is the equation of equilibrium here? So that all the forces are acting axially. So net axial direction force must be 0, then only that body is under equilibrium. So again, this R reaction that we don't know the direction, it is rightward or leftward. So arbitrarily we select it in rightward direction. Okay. So now we use the sign convention. The rightward force we take positive, and leftward force we take negative. Okay, by using that sign convention, this R is rightward, so that is positive R. 80 kilonewton, you see, this is the 80 kilonewton force, that is rightward, so again that is positive plus 80. The next force is 40 kilonewton, again that is rightward, so we take plus 40. And this is the 70 kilonewton force, right, that is in the leftward direction. So we use negative sign, so that is minus 70, and that is equal to 0. So this is the equation of equilibrium for this steel bar. And by using this equation, we are getting the value of R, that is minus 50 kilonewton. So minus means what? The direction which we take, that is rightward, it means that is opposite to that. So that is the meaning of this minus sign. So by putting the equation of equilibrium, we sense the correct direction of that reaction. So now we have to take the correct sense of the direction. So this R is 50 kilonewton and that is leftward. So by using the equation of equilibrium in that particular deformable body, we can find out any unknown force. So here the unknown force is a reaction, then easily we can find out by using the equation of equilibrium that the net horizontal force is equal to 0 or net axial force that is equal to 0. Now by knowing the reaction, we have to use the principle of superposition. So we have to divide this whole steel bar into three different sections. The first section, that is AB, the second section, that is BC, and the third section, that is CD. So we have to deal separately these three sections, and then we have to check the individual effects, and then we have to sum up, and that sum is the algebraic sum. So here first I talk about the section AB. So that section I am taking here. So this is the section AB. Okay, now we have to check in this particular section what are the forces. Okay, now you see, when you see this section, first we have to check the forces on its left face. The forces on its left face. So we have a 50 kilonewton force. You see, so in this AB section, the left face forces are 50 kilonewton. Okay, now you see the right face of that section. So when you see the right face, so here we have the three forces, this 80, 40 and 70. So in the right face of that particular section, we have three forces, 80, 40 and 70. Now you see the directions also. 80 kilonewton rightward, 40 kilonewton rightward and 70 kilonewton, that is leftward. So what is the net force in this particular phase? That is 50 kilonewton rightward. Already in its left face, the force is 50 kilonewton, that is leftward, and on its right face, the force is 50 kilonewton rightward. So you see, this section is also under equilibrium, and that is the static equilibrium concept, that if the whole body is under equilibrium, then its every section is also under equilibrium, and it is satisfied here again. Okay, so if you find out the elongation in any particular section, and if you see your equilibrium equation is not satisfied, it means there is some mistake. Okay, so definitely that section is also must under equilibrium. You see in the first section AB, so this 50 kilonewton force, that is a tensile in nature. So in this case we have the elongation. We have the elongation. The body will elongate. So whatever the deformation, that is taken as positive. Okay. Now the second section, that is the BC section. Now we have to see this BC section. So now again in this BC section, we have to see the force on its left face and on its right face. If you see this section, so in this section you have the two forces on its left face, 80 and 50. You see, these are the two forces on its left face in the BC section. That is 50, that is leftward, and 80, that is rightward. On its right face, if you see the forces, we have the two forces, 40 and 70. 40, that is rightward, and 70, that is leftward. Now we check the net forces on its both the faces. So now you see the net force in that BC section on its left face, that is 50 is leftward, 80 is rightward. So what is the net? That is 30 rightward. Now you see the forces on the right face of that BC section, that is 40 rightward, 70 leftward. So again what is the net? That is 30 leftward. Now you see again the section is under equilibrium. Two forces, same magnitude, opposite direction. So definitely this section is also under equilibrium. But you see what is the observation? This 30 kilonewton, that is the compressive in nature. So it means that body will contract. That body will contract. So it means its deformation, as a sign convention, we take negative. So this contraction always we take negative, because finally we have to do the algebraic sum of the deformations. Now the third section, that is the CD section. Third section, that is CD section. Now again we have to check the left face force and the right face force of that particular section. If you see the left face, in the left face you have the three forces, 40, 80 and 50. You see the directions also. 40, that is 80, that is rightward, 40, that is rightward, 50, that is leftward. So what is the net of these three forces? That is 70 rightward. On its right face, we have the 70 leftward. Okay, 70 leftward. Now again you see the equation of equilibrium satisfied. So again, but what is the observation? This body is also under compression. We have the compressive force of 70 kilonewton. So again, that deformation we take negative. Okay, so in this way, we deal with the individual sections, and then we have to mention the forces on that particular section on its right face and the left face. Then we check the equation, the condition of equilibrium, and also we have to check the bodies under tension or compression. Now finally I sum up. So this is the problem. The diameter 50 mm steel bar of the Young's modulus 200 gigapascal. So that gigapascal we have to convert into Newton per mm square. So 200 into 10 to the power 3. So that is 200 into 10 to the power 3 Newton per mm square. Okay. So now I sum up all the three. This is the AB section, this is the BC section, and this is the CD section. The first section, the force is 50 kilonewton and the body elongates. It means we have to take the positive sign of the deformation. The second section, that is under compression. Then we take the negative deformation. It means the body, that particular section contract. The third is again the contraction, because we have the compressive force. Again we take negative convention, sign convention. Okay, so now we have to use the principle of superposition. It means we have to check the individual effect of the deformations and we have to sum up with sign, and formula is PL upon AE if we talk about any individual section. So now this delta is the total deformation. Initially we don't know the net value is positive or negative, so we can say this delta is the axial deformation now in this particular step. Okay, so now the first one we take this AB section. You see this AB section. So what is the value of P for this section? This is 50 kilonewton. So that is 50 into 1000. We convert into Newton. So that is 50 into 1000 Newton. L, that is the length. So what is the length of AB section? That is 2 meter. So again we have to convert into millimeter. So that is 2000 mm. Now in the denominator we have the area. Area is what? The diameter is given. So that is a circular cross section. If the diameter is 50, so radius is 25. So that is pi r squared. So that is pi into 25 square. And E, that is a Young's modulus or modulus of elasticity. Its value is, you see here, that is 2 into 10 to the power 5 Newton per mm square. Gigapascal, you have to convert into Newton per mm square. So you see that value we put here. So this is the Young's modulus. So this is the value we take positive because that is the elongation in the first section, because 50 kilonewton is the tensile load. Now we check the second section. Second section is under compression. So we use negative sign because there is a contraction. So now again the second section or the BC section, what is P? That is 30 kilonewton. So that is 30 into 1000 Newton. What is the length of this BC section? That is 1 meter. So that is 1000 mm. What is the area? The area of all the three sections is same. And pi r square value is pi into 25 square. And E, again the material of the whole steel rod is same. And again E value is also same. That is 200 into 10 to the power 3 Newton per mm square. Now the third section, again we have the contraction. We use the negative value. And the force is 70 kilonewton. It is 70 into 1000 Newton. The length of CD section is 1.5 meter. So that is 1500 millimeter. The area is again same, that is pi into 25 square, and E value is also same, that is 200 into 10 to the power 3 Newton per mm square. So the first section under tension, so we have the elongation, the second section contract, the third section also contract. And when we sum up, this is the algebraic sum with sign. So we get this value of the delta minus 0.0891 millimeter. So now what is the meaning of minus sign? It means this contraction dominates over elongation. It means the net deformation that is in the form of the contraction. So the whole steel rod will contract with an amount of 0.0891 millimeter. If let us suppose that value comes positive, it means finally we have the elongation. But here, so this plus minus value will tell you finally you have the elongation or contraction. So in this problem, a steel rod will contract with an amount of 0.0891 millimeter. So this is the way to use the principle of superposition. Hope you understand the concept of elastic deformation due to the axial load as well as the principle of superposition. Thank you.